Okay, so this is our first unit lecture. This is going to be all of Unit 1 notes. I'm going to break it up into different pieces, but we're going to begin with talking about waves and sound. So this is Unit 1. So waves, a lot of people think they know what a wave is, and mostly they're correct, but the main thing about a wave is a wave's purpose is to move energy from place to place. It is not to move stuff. If it moves stuff, that is by accident or, some extra thing that the wave is doing. The wave's primary function is to move energy from place to place. We call that energy a disturbance. We say the wave is propagating, which means it's moving through a medium or moving through space. So we're going to start talking about waves in terms of talking about oscillations, because oscillations will be how we model the behavior of the individual components that make up the wave. So the two systems that we're going to examine are going to be the pendulum swinging back and forth due to gravity, and then the block and spring system, where the block is actually attached to the spring, not like in Physics 1, where the spring just pushed the block and the block went off and did its own thing. So that's going to create an oscillatory system also. Now, if you're going to have an oscillation, for something to be able to oscillate, it has to have a restoring force, meaning there has to be a force acting on it, trying to return the system to its equilibrium position. If it's not acted on by a restoring force, then there won't be any attempt to oscillate. It has to have this restoring force to be able for it to oscillate. Now, the simplest form, no pun intended since it's a simple harmonic oscillator, is the simple harmonic oscillator. It is a good model for a lot of the different oscillatory systems that we see. It turns out it's a good model to talk about light waves and sound waves and all of that. So we're going to focus primarily in this unit on simple harmonic oscillators and then just mention some things that happen with others. So the system that we're going to spend most of our time on is the block and spring system, where you have a system that has a block affixed to a spring, and it will, move back and forth. Now, let me see if this is going to work. Okay, I hope that you can see this. I think you can. So this is the lab that we're going to be looking at, but we're just going to look at the basic version of it. So in this case, we're going to look at where we have, say, for example, these are two springs that are identical right now, and we put a mass on one, and if we let it go, notice that that spring is going to oscillate back and forth with that mass on it. Now, the reason that this happens is, first of all, there is a spring force that you learned about in Physics 1, the Hooke's law force, that's causing that spring to try to return to its unstretched length, okay? Then the other thing that happens is this block or this weight here has momentum, all right? Because the mass can't just stop when the block gets to its equilibrium position, its momentum is going to carry it beyond that. Then what you have happen is it reaches equilibrium, it can't stop, so it goes beyond equilibrium, but then it's trying to pull it back. So the oscillation is due to the fact that you have this restoring force, and then you have this pesky mass on there with momentum that's not allowing the system to stop at equilibrium after one motion, okay? In this case, we have no friction, we have no external forces, so this thing would sit here and oscillate basically till the end of time if you wanted to. Okay, so let me get out of that and go back to our PowerPoint. Okay, so the block and spring system is actually fairly straightforward to analyze. We can use energy conservation, and then we're going to use that idea to develop our wave equation, which we'll see later on. So the block is used to compress or stretch the spring. In the case of the system that you just saw, when I hung the block on the spring, it extended the spring downward somewhat, extending it or stretching it. And then the spring force, or the Hooke's law force that you learned about in Physics 1, is our restoring force. In this case, F is equal to K times X. It's important to notice that this X is to the first power. That's going to be important because that's what makes it a simple harmonic oscillator. is the fact that the force is dependent upon the displacement to the first power. It's not squared, it's not square root. The force, F, is directly proportional to X, which is the displacement from equilibrium, with no square or cube or whatever exponent on the X. So as we let this thing move, it's going to overshoot the equilibrium point. And again, that's because of the momentum of the block. The block will not let this, or the momentum will not let the block stop at the equilibrium point. So if there's no friction to retard the motion, thing's going to sit there and repeat over and over and over. And that's what makes it a simple harmonic oscillator. So simple is because it's to the first power. Harmonic means it's symmetric on either side, and it's just going to continue on indefinitely. So remember that X is the displacement from the equilibrium position. So that equilibrium position may change. Like when I hung that block on that spring, that equilibrium position changes because it stretches the block. If I had just held it and let it be still, then my new equilibrium position would be that new stretched length. It's not going to try to go back to its unstretched length. Now, when I initially stretch or compress the spring, what I'm getting is what's called the amplitude. I give that initial stretch or initial compression the special name of amplitude, which we use a capital A. It's still measured in meters because that is the maximum displacement it's going to have from equilibrium. If nothing else comes along and pushes it, that's it. It's just like when you push somebody in a swing, when you push them, pull them up and you just let them go and you don't do anything else, they're never going to swing higher than where you started with them because that's all the energy that they had. So that's how it ties into energy conservation. The time for one complete oscillation, so start at a position, move over, come back. So start and finish in the same spot, so zero displacement, is called a period. So it's just like a class period is a time for one class, or a billing period is a time for one billing cycle. So this is a special value of T, so we indicate that with a capital T. We talked about that in rotational motion in Physics 1. So it's a special value of time called the period. Now, another thing that we didn't really mention in Physics 1, but that we're going to see a lot when we talk about waves, is frequency. So period is the time it takes for one oscillation. Well, frequency is the inverse of that. It's the number of complete oscillations per time period, usually per second. So the number per second we call a hertz. So when you see frequency, like in a musical instrument, or you talk about your computer chips having so many gigahertz or whatever, or your phones or whatever, that means the number of oscillations per second. So they're inverses of each other. Now, I mentioned that we could use conservation of energy to talk about this. So it is a conservative system if there's no friction, okay, and there's no external air resistance or anything like that. The only thing we've got going on is the Hooke's law force, and then sometimes we might have gravity if we have a vertical system. But energy is conserved in this system if there's no friction. So when I initially pull the spring over or initially pull the person up in the swing or whatever, I set the total amount of energy of the system. And that's what you're going to see in that spring lab that you'll do next week. And I'm going to make a little video to go along with that that shows how to do a little bit about that lab so you can answer some questions, get some questions answered if you have any, since I won't be able to be with you in the lab. So I established the total energy when I established the amplitude of the motion. So if you remember, the energy of a spring is 1/2 kx squared, where x was the displacement. So the initial energy, or the total energy, then depends on the amplitude. So I can replace x with a and get 1/2 ka squared. So that's the initial total energy, or in this case, it's also the initial spring potential energy, because when I pull that spring over to the side and I'm holding it still, that means I've got no kinetic energy, I've only got potential energy. And then I'm going to let it go, and it's going to move, and it's going to convert all that initial spring potential energy into kinetic energy at some point. All right. Just like when you have the ball and you raise it up and you drop it down, how high you raise it is going to determine how much kinetic energy it has right before it hits the ground. So the same thing with the spring potential energy. So as the block overshoots, so you go through the equilibrium position. At the equilibrium position, the definition of equilibrium is there's no displacement. So if I start over here at the amplitude and I slide to equilibrium, I've converted all my spring potential energy into kinetic energy. Then I've got this problem of this momentum, so it's going to overshoot, and now it's going to start to slow down because the spring is going to start to pull back on it. So as it moves past the equilibrium position, now I'm converting all that kinetic energy I had at equilibrium back into spring potential energy till eventually it's not moving at all. So that's why it's symmetric on either side of equilibrium, because I have to convert all that energy back into spring potential energy. So what I can do, just like when I had the ball falling, I can use energy conservation to find the velocity at any point. I really should say speed. It's not really the velocity. I should say speed here, because the speed on, like if I'm 2 centimeters on the left side of equilibrium and 2 centimeters on the right side of equilibrium, it doesn't matter. It's going to be the same speed. Okay, so I really should say speed there, but I can use energy conservation to find the speed. So I kind of already mentioned this, but where is the block going the fastest? Whereas I've taken all the spring potential energy and I've converted it into kinetic energy. Where is that at? Well, it's at equilibrium. It's at equilibrium because I have no displacement at that point. So all the energy I've got is going into kinetic energy. Now, I can use the motion of this block and spring to develop something called the equations of motion. And I'm going to make a little separate video about something called the reference circle, because I've got to do some drawing. Okay, I've got to do some drawing, but I'm going to make a little separate video about the equation of motion, or about the reference circle and how it relates to the equation of motion. But I can take the motion of a block and spring and I can use that to map rotational motion. And once I do that, I can develop what's called the equation of motion, which is actually a more powerful analysis than energy conservation. Because when I talk about equation of motion, that really truly is about the velocity and the displacement and all of that. Not only does it tell me how fast it's going, it tells me which direction it's moving, which is more powerful. And the nice thing about this is the equation of motion for a block and spring will work for any simple harmonic oscillator, or the style, I should say, the style of equation of motion of the block and spring will work for any simple harmonic oscillator, because they all have the same form. They all depend on that displacement to the first power. We're going to end up with an equation that relates displacement, period, frequency, and amplitude. So basically, you can tell everything about a wave by looking at its equation of motion. You can get all the information you need to know if you know how to pull it out of there to get that information. So we're going to look at a block and spring system because it's just easier to see, but it also works for things like simple pendulums, and it's going to turn out that it works for sound waves and light waves and any simple harmonic motion type wave. Now the nice thing about this, and even though we don't do calculus in here, is I can take the equation of motion and I can take a derivative. So if you remember that derivatives are really rates, remember from physics 1 that velocity was the change in displacement over the change in time. So it's the rate of change of displacement. So if I take a derivative of a position function, that gives me a velocity. And acceleration was the rate of change of a velocity. So if I take the derivative of a velocity function, that gives me the rate of change of that, which is the acceleration. So I can use calculus now to describe the velocity and the acceleration if I want to, okay? And that actually is truly velocity and acceleration because it tells you the magnitude and the direction of the thing's motion, which is more powerful. So remember I said energy was not as powerful because a displacement of 2 centimeters on either side of equilibrium gave me the same speed, but there's 4 potential velocities. You could be 2 centimeters going this way, or you could be at 2 centimeters going this way. Same thing over here. You could be moving further out, or you could be coming back in. So there's 4 possible values of velocity that I can't discern from the energy expression, but I can get it if I have the equation of motion, and that's a more powerful tool. Now, one of the things that does sometimes happen is in the really real world, we have friction. And so friction, what it does is it robs energy from the system. So each time that thing's oscillating and it's dragging across the floor, whatever it's doing, or there's internal friction in the spring, we're going to lose amplitude. So the amplitude will eventually decrease until it just stops. And this is just like if you push somebody in a swing and you give them an initial push and you don't do any more, eventually it's going to stop because there's internal forces that are going to stop the motion. So we call that damping. And there's different types of damping, and it's fairly complex to try to mathematically analyze it, but understanding what happens is not hard at all. Damping is not necessarily bad. Say, for example, in your shock absorbers in your car, okay? You want the motion to be damped there. The whole point of the springs or struts or shock absorbers on a vehicle is they stop the oscillation. So if you're driving down the road and you hit a bump, you want there to be some give there, or it would be a very unpleasant ride. But if the car gives too much, or it gives and then it continues to oscillate, then you can't keep your car on the road. Okay, so if your suspension is getting bad, you know how difficult it is to keep that vehicle on the road if you hit a pothole or you go over a train track or something like that. So you want a damping system on that. There's situations like in earthquake mitigation systems in buildings. They basically are on big springs or big movable platforms that balance out the motion of the earth. Say, for example, in Tokyo. Japan is one of the most tectonically active countries in the world. You don't hear a whole lot about when they have earthquakes because all of their technology has been geared toward earthquake mitigation. And those buildings will rest on those basically shock absorbers, and you want to damp that motion because you don't want your building to fall down. So eventually it will cease, and I've spelled eventually wrong, but eventually it will cease the motion. Now there's different types of damping. There's critical damping where there's a gradual decay, there's over damping, and then there's under damping. Over damping is where you stop it in a hurry, okay? And then under damping is where it slows, but at a much slower pace than critical damping. And the calculations for that are not something we're going to do, but I just want you to be aware that that does exist. Okay. See if I can pull up my examples here. It may not let me. Okay, so let's see if this will pull up. So this is just a little cartoon of a damped system. Now what they're doing is they're letting this thing oscillate, and they're graphing the motion. So as it swings, you'll notice that this amplitude feature gets shorter. So this kind of goes along with what we had with the reference circle that you're going to see in that video, where this is a simple pendulum swinging back and forth. And see how that peak is lower there, or smaller? So that's because of the damping, and eventually it will stop swinging altogether. Okay, so we can transfer this to the concept of wave motion. So this is where I'm going to stop the video and break it, and we'll start a new video for this portion.